Evaluation of definite integrals by substitution. In the previous session, we learned how to find definite integrals, right? Now, in integrals, we have studied the method of solving by what? Substitution also. How can we use that method in definite integrals to solve? Suppose we have a question like this, that is from 0 to 1, tan inverse 1 plus tan inverse x divided by 1 plus x square dx. So they are asked to find out what is integral 0 to 1 tan inverse x by 1 plus x square. So you can see here it is directly a definite integral because it is from limit 0 to 1. Now you have inside tan inverse x by 1 plus x square. In integration, the basics of integration, we have studied the method of substitution. Using that same method here, can we solve it? Yes, because you know that derivative of tan inverse x is what? Nothing but 1 by 1 plus x square. So put that over here, that is put tan inverse x is equal to t. So when you put tan inverse x is equal to t, what do you get? You get 1 by 1 plus x square dx is equal to dt. Yes. So when you put tan inverse x is equal to t, you got 1 by 1 plus x square dx is equal to dt, which is this one, that is dx by 1 plus x square. So you can put that as what? Dt now. So now I'm putting that as dt, and tan inverse x, what I'm going to do, I'm putting that as t. So can you write it as integral t, that is tan inverse x is t, and dx by 1 plus x square is what? Dt. So you can write as t dt. But there is a small issue. What is that issue? The limit, that is the lower limit 0 and the upper limit 1, which was with respect to the variable what? X. What we have done here? We have substituted that variable x and put a new variable which is t. So what happens to the limit? The limit also has to change in terms of the new variable, that is t. So don't forget, whenever you are doing integration by substitution in definite integrals, always remember that you have to change the limits also. So what do you have to do? Change or convert the limits, that is the upper limit and the lower limit, based on the new substitution that we have given. So I have given tan inverse x is equal to t. So I have a lower limit 0 and upper limit 1. So x is equal to 0 and x is equal to 1. Yes. Now I have substituted tan inverse x is equal to t. So what happens is, when I put 0, that is the lower limit, I get tan inverse 0 is equal to t, or that is nothing but 0. Yes, because tan inverse 0 is 0 itself. So even when the lower limit now in terms of x is 0, the upper limit is also, the lower limit in terms of t is also what? 0. And when x is equal to 1, the upper limit, tan inverse 1 is equal to t based on our substitution. What is this tan inverse 1? That is pi by 4, because you know that tan gives an output 1 when it takes an angle, how much? Pi by 4. So the t should take a value, how much there? Pi by 4. So now you have the lower limit as 0 and the upper limit as how much? Pi by 4. So what do you have to do? Just write it as 0 to pi by 4. Understood? So that is the only difference when it comes to definite integrals. So in definite integrals, when you do substitution, use substitution and change the limits also, lower limit and the upper limit. So when I do that and integrate it, that is t dt, integral will be t square by 2 from which interval? 0 to pi by 4. And when you do that, you will be getting it as pi square by 16 minus 0 square, and there is a 1 by 2 outside because it is t square by 2. So the final answer will be pi square by 32. So this gives us the final answer for the question integral 0 to 1 tan inverse x by 1 plus x square. So remember, whenever you are evaluating a definite integral using the method substitution, make sure you change the limits also. That's the only difference. Now let's do another question. Now the question here is integral 0 to pi by 2 root sine theta cos raised to phi theta d theta. So this is the question. So you have to integrate this one, right? Again, you can see it is definite integral because it is having limits from 0 to pi by 2, and you have inside root sine theta, and then what is the next thing? Cos raised to phi theta d theta. Can we use substitution here? We can try using that substitution, right? If I put in terms of the sine theta as something that is t, and if I take the derivative, it is going to give me cos theta. But I have cos raised to phi theta. So what should I do there? So I will be first splitting that and writing it as root sine theta, and cos raised to 5 theta I'm going to write as cos raised to 4 theta into cos theta d theta. Now again check, look here, you have cos raised to 4 theta. What is this cos raised to 4 theta? Is it the square of cos square? Yes. So what I do here is I'm writing cos raised to 4 theta as cos square theta the whole square. And again, what is this cos square? Is it 1 minus sine square? Yes. So what I do next here is I write it as 0 to pi by 2 root sine theta cos square theta. I'm writing it as what? 1 minus sine square theta the whole square, and then you have a cos theta d theta. So the question which was in this form, before I even substituted it, I changed it into this form. Now what I'm going to do here is I'm just going to put the sine theta is equal to t. So when I put sine theta is equal to t, I get cos theta d theta is equal to dt. So this cos theta d theta becomes the new integrand, that is dt. Now what you should change the limits also. So don't forget that. So you have 0 to pi by 2. So theta is taking 0 and theta is taking pi by 2. And when you take like that, you get sine 0 which is equal to 0 and sine pi by 2 which is equal to 1. So the new lower limit and upper limits are what? 0 and 1. So write it in this form, that is integral 0 to 1. And what is this root sine theta? It is now in root t form. Yes. 1 minus sine square theta the whole square. Can you write as 1 minus t square the whole square? Yes. And what is this cos theta d theta? It is dt. So you can write as dt. So now you have 0 to 1 integral, that is root t into 1 minus t square the whole square dt. And now you just have to expand the whole thing, right? So I'm taking this, and if I expand, what will I get? So when I expand this one, I will be getting it as integral 0 to 1 root t into what is 1 minus t square the whole square? It is 1 plus t raised to 4 minus 2t square dt. And again you multiply that inside, you will be getting root t plus what is root t into t raised to 4? It is t raised to 4 plus 1 by 2, that is t raised to 9 by 2. So t raised to 9 by 2 minus 2t square, and into root t you will be getting as 2t raised to 5 by 2 dt. So this is what you get. Root is nothing but t raised to 1 by 2. So what will be the integral of root t? It will be t raised to 3 by 2 by 3 by 2, or it is 2 by 3 t raised to 3 by 2 plus t raised to 9 by 2 integral will be t raised to 11 by 2 by 11 by 2. So that is 2 by 11 t raised to 11 by 2 minus 2, and t raised to 5 by 2 integral will be t raised to 7 by 2 by 7 by 2. When you write it here, you will be getting as 2 into 2 by 7 t raised to 7 by 2 from the limit 0 to 1. What is the final thing that you do? Apply the limits. So applying the upper limit, you get 1 over here. So you will be getting as 2 by 3, 1 raised to 3 by 2 minus 0 raised to 3 by 2, which is nothing but 0, plus 2 by 11, t raised to 11 by 2, that is 1 raised to 11 by 2 minus 0 raised to 11 by 2, again 0, minus 2 into 2 by 7, that is 4 by 7, t raised to 7 by 2, or 1 raised to 7 by 2 minus 0. And when you do that, again 1 raised to any number is 1 itself. So you will be having only 2 by 3 left. So 2 by 3 plus 2 by 11 minus 4 by 7. Take the LCM, 3, 11 and 7. So all are prime numbers. So the LCM will be something around 77, that is into 3, which will be nothing but 231. So you have to finally calculate all these things. That is 2 by 3. You have to multiply with 77. So you will be getting it as 2 into 77 will be 154. Yeah, 154 by 231 plus 2 by 11. You have to multiply with 21. So you will be getting as 42 by 231 minus 4 by 7. You have to multiply with 33, and 33 into 4 you will be getting as 132 by 231. So 154 plus 42, 196 minus 132, you will be getting it as 64 by 231. So using all the final calculation, that is just after substituting, you have to change the limits and directly apply the integral and substitute the upper limit and the lower limit, and you will be getting the final answer, which is 64 by 231. Now let's do one more question and wind up the session. So we have a question over there here, that is integral 1 to 2 e raised to 2x 1 by x minus 1 by 2 x square dx. We have studied a form where e raised to x into f of x plus f dash x dx, that is integral of e raised to x f of x plus f dash dx is nothing but e raised to x into f of x plus c, right? But here is it in that form? Here, first thing that you have to notice is it is not in the form of e raised to x. Here itself, you have e raised to 2x, double of x, right? So what you have to first do is you have to change that double, that is 2x, to a singular form. So what you have to do first here is take 2x and put that is equal to t. I'm just trying that. So when you put 2x is equal to t, I'll be getting 2 dx is equal to dt, or from that dx is equal to what? dt by 2. Fine. And now, since I have substituted 2x is equal to t, look for the limits, upper limit and the lower limit. That is 1 is the lower limit and the 2 is the upper limit. So when I take x is equal to 1, I will be getting t is equal to 2 because 2x is equal to t. When I take x is equal to 2, I will be getting t is equal to how much? 4. So the new lower limit is 2 and the upper limit is what? 4. So it will be from 2 to 4, e raised to 2x will be in terms of t, right? So e raised to t into 1 by x. So what will be 1 by x now? Because I have written 2x is equal to t, can I take x is equal to t by 2? Yes. So when I substitute that over here, I will be getting 1 by x or 1 by t by 2 or 2 by t minus 1 by 2 x square. So 2 into x is now t by 2. So t square by 4. And that 4 goes up here. Yes. And dx, in terms of dx, I have now what? dt by 2. So now doing all the calculations here, this 2 gets cancelled. I can write as 2 to 4 e raised to t, 2 by t minus 2 by t square dt by 2. There is a 2 in the numerator as well as in the denominator. So I can cancel all this, right? And I can even write it as integral 2 to 4 e raised to t, 1 by t minus 1 by t square dt. Yes. Now if I see, this is in the form of what? E raised to x into f of x plus f dash x dx. That is, if it is in this form, I can easily write it as integral, that is e raised to x f of x plus c. Yes. Yeah. So here I can see it is e raised to t into 1 by t minus 1 by t square. Is 1 by minus 1 by t square the derivative of 1 by t? Yes. So this minus 1 by t square is the derivative of 1 by t. So this can be taken as f of t, and this will be definitely f dash t. So I can now write this directly as what? 2 to 4, that is integral 2 to 4 e raised to t 1 by t minus 1 by t square. I can write it as e raised to t into 1 by t, and from limit where? 2 to 4. And when you apply the limit, that you will be getting it as e raised to 4 by 4 minus e raised to 2 by 2 plus c. So this gives us the final answer for the question integral 1 to 2 e raised to 2x into 1 by x minus 1 by 2 x square dx. So here e raised to 2x, it was in that form. I substituted 2x which is equal to t, and then I could convert that into a standard integral that we have studied earlier in this chapter. And I could evaluate and find out the final answer for this question. Now, there is a plus c that I have written over here. That plus c is not needed because we're studying about definite integral. So e raised to 4 by 4 minus e raised to 2 by 2 is the final answer for this question. Now let me draw a graph over here, and let's see what that graph has got to do with this chapter. Suppose I'm drawing a graph of sin x. So I have over here the graph of sin x. So this is a graph of sin x that I've drawn here on the positive side of x-axis only, right? So now I'll be noting it as 0. This one is pi, and here I have 2 pi, then I have 3 pi, 4 pi, like that. Now what happens over here is, if I take from 0 to pi and 0 to, that is from pi to 2 pi, if I just shade the area, I'm just shading the area from here. So 0 to pi, this is the area, right? Pi to 2 pi, this is the area from pi to 2 pi. And from 2 pi to 3 pi also I'm shading just the area of there. Yes. For this, so this graph over here is y is equal to sin x. So I've just shaded the part from 0 to pi, pi to 2 pi, and 2 pi to 3 pi. Can I say the area which is under 0 to pi, just look at the area from 0 to pi, that is integral 0 to pi sin x dx, will that be same as the area from pi to 2 pi sin x dx? The curves are symmetrical enough so that the areas under 0 to pi and pi to 2 pi will be the exact same. Only difference is that it can be negative because it is lying under the x-axis. But for finding the area, you just have to take the modulus of it, right? So when you take the modulus, it will be anyway positive. So the area or the magnitude of area will be equal from 0 to pi and pi to 2 pi. That is, I can write 0 to pi area is same as pi to 2 pi. So that means in definite integrals, whenever you have a limit in integral, the areas can be the same or the values can be same or sometimes can be double, which leads us to the properties of definite integrals, which you will be studying in the next session. For the time being, we'll just have a quick recap of what all we have learned.
Manorama Horizon. Learning made simple.